All right, everybody, it's that time of year again where we're going over the AP Physics C free response questions. Now, out of the four sets that were released, the two mechanics and the two electricity and magnetism ones, I have actually looked at one of the two mechanics free response questions. Now, this one here is set one. And so if I scroll down to this is actually the one that I have not looked at yet. So this is the one that I'm actually going in blind on. I have, however, looked at set two. Most of it, I think, is going to be pretty similar to set one. But yeah, let's go ahead and take a look at this then. So here, what we have is we do have block, and then you have it's attached to a spring, right? The spring is compressed a little bit. And then that's going to release the block, cause it to go on something with friction. And then if we go on to the next page, we'll be able to see the rest of the prompt, where it does actually stick to block B, and it's looking as though block B is actually attached to a string. And so after that, it's actually going to act like a pendulum then, where it actually will swing back and forth. Let's see if I'm right though. So part A, part one says to derive an expression at time t1. So that's referring to after the spring has actually gone back to its equilibrium distance. So there's no friction yet. And so if we actually solve this equation here, right, what we have to do to derive an expression for the speed is we actually have to use conservation of energy. So we'll say that the initial spring potential energy should be equal to the kinetic energy of the block after the spring has gone back to its normal length then. So we have 1 half kxc squared for spring potential energy will equal 1 half mv squared, right, for that speed that we're trying to find. So again, all of the initial energy is spring potential, and that's all transferred to kinetic because there's no friction yet. And so therefore, we get that V is going to actually just equal xc times square root of k over m, which is something that you've probably seen before for simple harmonic motion problems that involve energy. But yeah, there we go. Nice and easy then. So that means that we can actually move on to part two then, which is to derive an expression immediately after the collision. Now, this is where you might kind of fall into a trap because you don't actually want to use the velocity you found in part A. You don't actually want to use that velocity that you found in part A for the collision because at this point, after time t1, block A is undergoing some area with kinetic friction. So therefore, it's actually going to be slowing down a little bit. So all that being said, then we actually need to figure out how fast the block is going to be going right before the collision, how fast block A is going to go right before the collision in order to be able to solve this problem with conservation of momentum then. So I'm actually going to go to full screen here just so I have a little bit more room. And let's go ahead and clear all of our annotations so that we can do that. So going back to part A, right, I'm just going to go ahead and write my expression down for that. We did find that V is equal to xc square root of k over m. Right, now if we want to find the speed of block A before the collision, we do have to use either energy or work or impulse for that. However, I prefer to use work done because it actually gives us the distance. So what I can say is I can say that the work done by friction is going to equal F times D, right? So the work done by friction is equal to friction force multiplied by the distance. So that's going to be equal to negative mu times normal force multiplied by D. And in this case, the normal force is actually going to be equal to mg. So we get negative mu mgd for our work done by friction. So what that means is that the kinetic energy of A before the collision is actually going to be the kinetic energy of A before it experienced friction plus the work done, so minus mu mgd then. So we're going to have 1 half m times v squared. So if I square that velocity we got from part A, we get xc squared times k over m. The good news is that the m's will cancel out here, so we can simplify that down. Minus mg mu mgd then. So what that means is that the kinetic energy of A before the collision is going to equal 1 half kxc squared minus mu mgd. all of that stuff has to equal 1/2 times the mass of block A times its velocity before the collision. Not after, but before the collision. Remember, we can't say that energy is conserved during the collision because this is inelastic. And this question is just as tedious as the set 2 question, actually. This is going to be a terrible expression for us to use conservation of momentum with. So that's fun. Instead, I think what I'm going to do then is I'm actually going to turn kinetic energy into something that relates to momentum of block A before the collision, p squared over 2m. The reason I can do that is because if I take momentum is equal to mass times velocity, I square that, I get m squared v squared, and then if you divide that by 2m, then you're going to get kinetic energy. You're going to get 1/2 mv squared out of it. So p squared over 2ma, right, which is just m, right, that's fine, is equal to, that's all going to be equal to 1/2 kx squared minus mu mgd then. Now, if we, from that, we can then find the momentum, the total momentum of the system right before the collision. So going back up to this problem right here, it does look like block A has mass m, and it does collide with a block of mass 3m then. So what we can say is, if we use conservation of momentum then, we can say that PA is going to equal 2m all square root, by the way, from that expression up above. That's going to equal 2m times 1/2 kxc squared minus mu mgd. And this is so bad. This is just tedious at this point. Like the actual solution to this question is easy. You're just using work energy theorem, right, and conservation of momentum, but these expressions are just so nasty. All right, and so all of that then has to equal 4m times VAB because of conservation of momentum then. So therefore, right, VAB is going to equal all of that stuff in the, in the square root divided by 4m. That is just horrendous. Yeah, I'm not even going to bother to simplify that. I'm just going to write it out, divide by 4m, just so we get our final answer there. So VAB is equal to square root of 2m 1/2 k xc squared minus mu mgd. Again, all of that is inside a square root, and then you divide that by 4m. That is horrendous. All right, okay, that's no fun. All right, anyway, moving on to part B, you have to make a sketch of kinetic energy as a function of time and use the principles of work and energy to justify all of that. All right, so I'm actually going to kind of justify this as I'm going along. So from 0 to time t1, what we know is that the force is actually going to be kind of related to something along the lines of a cosine function. The reason why we know that is because this kind of follows what a spring would do in simple harmonic motion if you start it compressed. So it's going to look like a cosine function because everything follows sine or cosine in simple harmonic. Therefore, velocity is going to be related to sine of t, and therefore kinetic energy is going to be related to sine squared of t then. So all of that kind of works with simple harmonic motion then from 0 to t1. So a sine squared function looks very similar to a sine graph, and we're going to get something along the lines of that. All right, from time t1 to t2 then, what we do know is that the force on the block is going to be constant, right? The force is going to be constant, and then therefore you have a constant acceleration. So therefore, what the velocity time graph would look like is that would actually end up looking like a straight line. It's a constant less than 0 for the acceleration, so the velocity is decreasing as time goes on. And if I take like a velocity being proportional to negative t, what that's going to mean is that kinetic energy is going to be proportional to t squared then. Keep in mind that kinetic energy is proportional to speed, not velocity. So what I would expect is I would expect a kinetic energy to look like a quadratic function then as well. And I'm actually going to label these that it goes like sine squared of t, right? And then for the second one, it goes similar to t squared. And then from 2 to 3, there's no net force, right? So therefore, there's no work done. And therefore, you're going to have therefore you're going to end up having just a straight line. So net force is equal to 0, right? That means that there's no work done. Therefore, k is equal to a constant then. And there you go. That's what the graph should look like in this case. All right, let's go ahead and move on to the next page. I believe we have one more page left of this question. Yep, there we go. You've got something instantaneously coming to rest. Okay, when it reaches the maximum angle, and then it oscillates with some frequency. Okay, so you repeat the equation, you repeat this procedure with a string of length 2L, and you're asked what's going to happen to the frequency of oscillation. This is very easy. How I know this is easy is because this is a pendulum, and a pendulum, the period goes like 2 pi root L over G. So therefore, the frequency, which is equal to 1 over period, is going to be proportional to 1 over the square root of L, right? 1 over the square root of length. Since L increases, the frequency is going to decrease then. So therefore, f of 2L should be less than f of L then. There we go. Nice and easy. All right, moving on to the second question. It looks like this one's a forces question. So we're taking a look at a cylinder dropped from rest, and you have quadratic drag on it. Derive but do not solve a differential equation that could be used to describe this, determine the speed. That's easy because this is a mechanics question. Anytime you have to create a differential equation, you always have to start with Newton's second law. But since we're working with velocity and not acceleration, we change a to dv dt then. What I'm going to say is that down is going to be my positive direction, right? So therefore, what I can say is that the net force is going to be mg minus bv squared will equal m dv dt then. And there's our differential equation. We don't have to do anything else. We do not have to solve it, nor would you be able to solve this with anything other than partial fractions or some other methods that you haven't covered in Calculus BC. All right, but there's our differential equation. We can move on to the next page now. So let's go ahead and clear this. All right, you now have Vmax versus time. You're given a velocity versus time graph here, and you're asked to sketch the earliest time at which the drag force is equal to the weight. That's easy. It's right when you experience terminal velocity. Let's label that T1, as the problem says we should. Justify the location. When V is equal to V max, you have no acceleration. Therefore, so dv dt is equal to 0, right? And F net has to equal 0 then, because F net is related to acceleration. That means that F drag has to be equal to the magnitude of the weight of the cylinder then. There we go. All right, rather than dropping it from rest, we throw the cylinder upwards with an initial speed. And what we have to do then is allow it to fall to the ground and indicate whether the magnitude of the maximum downward speed would be greater than, less than, or equal to. It has to be equal to because the drag force, because the object changes direction, sorry, not because the object changes direction, but because the drag force has to equal the magnitude of the weight force at this maximum downward speed. And mg is independent of initial velocity. There we go. Nice and easy with that. All right, second question, sorry, not second question, the graphing part here. You're given max speed squared as a function of mass. You're asked to determine a draw a best fit line. All right, obviously you guys would have had to use a ruler for that. Since I'm online right now, I'm just going to approximate it. Yeah, I'd say that looks pretty good. There's my best fit line. All right. not great, but not terrible. I'll take it, and hopefully you'll be fine with that. All right, use the best fit line to calculate an experimental value. Well, we know that this V max occurs at terminal velocity. So what I know then is I know that mg has to equal bv squared, b max squared at this maximum velocity. So if I divide by mass and I divide by b, what I'm going to get is that I'm going to get g over b has to equal the slope, which is equal to change in Vmax squared over change in mass. So in other words, rise over run for my graph. So therefore, I actually have to calculate the slope of this. And then if I take g over the slope, right, that's going to actually give me my value of b then. So my slope, I can calculate using two data points. Looks like 0.1 and 2 is one good data point. So that's going to be my first data point right here. And then the second one, there's not really a good point, but here's my first one. And let's make this one right here my next one. So that's going to be 0.22, comma 4. 0.224. So my slope then is going to equal 2 over 0.12 then. So therefore what b is going to be is it's going to be 10 for g times 0.12 divided by 2, or 1.2 divided by 2. That's 0.6 over 1, or just 0.6. And the units for this are, let's see, the units for this are going to be newtons divided by meters per second squared, because force was equal to b times v squared then. So newtons times second squared over meter squared. There we go. So again, since F is equal to bv squared, F as units of newtons divided by speed squared, and you get your units for b then. There you go. All right, let's go ahead and move on to the next page. Clear our drawings as usual. All right, and you now have two sets of cylinders, and you're trying to determine if the length of the cylinder is going to impact the maximum speed. What could you plot? This is not too bad. You just have to plot that maximum speed versus length of the cylinder. All right, this briefly described part honestly is, I don't know, it's kind of easy to tell, right? If max speed is not a constant, as you vary the length of the cylinder, then they have some correlation. Find it by using a power fit and then linearizing the graph according to your power fit. There we go, easy enough. All right, I don't really know what they want from that. I mean, you know, you could do different stuff. You don't have to do max speed versus length of the cylinder. You could do stuff related to drag force if you wanted to, probably. I don't know. I feel like my two quantities are pretty trivial to describe how they would be used to determine the relationship. All right, anyway, let's move on to our rotation question. I know it's rotation because I see the word pivot and I see that there's a uniform rod, and this does not really look all that fun. All right, okay, so you have a block, you have a string, you have a pivot, you have a rod, right? There's a center of mass at point C. Yeah, that makes sense because that's like the halfway point. And what we have to do is draw and label the forces that are acting on the rod. Okay. All right, that's not too bad. It doesn't look anywhere near as confusing as what set 2 had. But what we have is we have gravitational force of the rod, which acts on the center of mass. We'll call that Fg. We've got tension from the string acting on point Q, so we'll call that Ft. We've got the force from the 3m, which we're going to have to draw 3 times as long as the force of gravity on the rod because it has 3 times the mass, so that's fun. We'll call that F3m. And then you have a hinge force as well that's going to keep this in static equilibrium. That hinge force is going to be pretty big, I guess. So it's going to have to go up and to the right. Sure, probably something along the lines of that. I'm going to call it FH for hinge force. essentially just net force has to equal 0. So I'm going to write that off to the side then, just in case my arrows are not equal length. But I tried to make them as good as I could so that everything cancels out. All right. Okay. Next page. How much do we have left? Okay, just 2 more pages left on this one. So I don't know if you guys can tell, but I'm really not liking how tedious some of these questions are. So all right, okay. So in figure 1, point P is located 3/8 from the pivot, and point Q is located 6/8 from the pivot. Oh, come on. Derive an expression for the tension in terms of all of that stuff. Okay, since we don't want to have to include the hinge force, we're probably going to be dealing with torque then. Sum of all torque should equal 0 because this is in static equilibrium. And especially because it gave us distances, that kind of tells us that things are going to be important for this. Torque is going to be important for this. Okay, so we have that the 3M is going to try to get the rod to rotate clockwise, so that's actually going to be a negative torque. So we're going to have negative 3/8 L times 3mg multiplied by sine of theta for the torque caused by the 3m mass. Let's see. Here's our angle theta. Again, I know that this is figure 2, but the angle's still the same in figure 1 and figure 2, and I should probably confirm that. Yep, it is. Okay, so that's fine. All right, probably best to confirm before I get too far into the problem. Minus L/2 times mg sine theta for the gravitational force of the rod, right, plus 6/8 L times ft. And then the angle that we're going to have is 90 minus theta right here if the string is just completely horizontal then. So instead of sine of theta, it's actually going to be cosine of theta then. So cos theta. There we go. All right, let's try to simplify this down then, I guess. All of that has to equal 0. So that means that you get 9/8 mg and 9/8 from the first term, and then 1/2 from the second term. 1/2 is 4/8. So you're gonna get 13/8. This is fun. MGL. I'm not enjoying this, guys. Sine of theta. All has to equal 6/8 L ft cos theta. Yeah, let's solve that for tension, I guess, because we're supposed to, right? Ft is going to equal 13 mg over 6 times tangent of theta. Okay, that's not terrible. At least I'm glad it simplifies down nice. All right. There we go. Okay, the original string is now replaced with a longer string. We have figure 2 now. The angle remains the same then. And the question is, how is the new tension going to compare to the old tension then? Okay, so what I am seeing here is that the angle theta is still remaining the same. The angle theta is still remaining the same, but now tension has a vertical component. However, I do think that it's actually going to be the same. I think that the tension is actually going to be the same. And what's going to happen is that the hinge force would just end up picking up the slack. Now, the reason why I think tension is going to remain the same here is because the angle is remaining the same. So from our previous question, from part B, right? Actually, no, it's not going to remain the same, is it? Let's see. So the angle between the radial line and the string is actually increasing. So the torque caused by tension okay, so the torque caused by tension in the is going to go something like 6/8 LFT times sine of whatever angle you have. I'm going to call it phi, and this is our angle phi right here. Right, so the higher torque, you can't have a higher torque because the torque caused by the two first forces at points P and C, that's not changing. So torque has to remain the same, your sign of angle contribution goes up, therefore tension actually has to go down. No, sorry, tension actually does have to go down. Okay, so so the new tension is going to be less. New is less, right? Okay, there we go. From part B, the torque caused by tension has to remain the same. Since the angle between the radial line and tension increases, and 6/8 L equals R is constant, Ft new must be less than Ft original then. There we go. Okay, I'm confident with that. All right, non-uniform rod. Oh, here we go. It's our linear mass density stuff, and we have to calculate both the mass and the inertia. This is not too bad. Mass of the rod is just given by integral of lambda dx, which is because that's equal to integral dm, right? So integral lambda dx then is going to equal from 0 to 1/2 of a plus bx. So that's going to be 6 plus 10x dx. So that's going to give you 6x plus 5x squared from 0 to 1.2. So that's going to give you, the 0 is not going to matter. It goes away. So you get 7.2 plus 5 times 1.2 squared. And they're really going to make me pull out a calculator for this, but I'm not going to, because 1/2 is 6/5. When you square that, you get 36/25 then. So one of the 5s will cancel. So you end up with 7.2 plus 36/5. And 36/5 is 7.2. I think I'm doing that correctly. Is it seriously another factor of 7.2? Shoot, now I'm doubting myself. 36 over, yeah, it's 7.2 again. So you're just gonna get 14.4 kilograms. Kilograms. Yep. There we go. Okay, fun. All right, calculate the rotational inertia of the rod about the pivot then. We cannot just use 1/3 ml squared because this is a non-uniform rod. So we have I is equal to integral x squared dm, or integral of x squared lambda dx, right? So that's going to give you integral of from 0 to 1.2, that is. So integral from 0 to 1.2 of 6x squared plus 10x to the 3rd power dx, which is 2x cubed plus 5/2 x to the 4th, 0 to 1.2. And if I plug that into my calculator, 1.2 cubed is 1.728. So if I multiply that by 2, that's going to give me 3.456 plus, and then 1.2 to the 4th power is 2.0736. Multiply that by 2.5, you get 5.184. Sorry, I'm doing all of this off screen, just so I don't have to switch between different screens. All right, so you get a total inertia of 8.64 kilograms times meters squared. And that's the end of set 1 then. All right, so all in all took us about 32 minutes. Again, I haven't looked at this question before, these questions before, so I went into these ones blind. Set 2 should be a little bit faster again because they're very similar to set 1, and I have actually looked at them before. But thank you for watching, and I'll see you back here for the set 2 free response questions then.